Good day, everybody. My name is Talbot Brooks, and I am the immediate past president of the Geospatial Information and Technology Association. We are bringing you today's webinar from Dr. Keith Clarke out at the University of California, Santa Barbara. He's going to present Geographic Masking, Motives, Methods, and Utility. Dr. Clarke is a research cartographer and professor with a master and a PhD from the University of Michigan, specializing in analytic cartography. He is the author of 3 textbooks and 8 editions and over 250 book chapters, journal articles, and papers in the fields of cartography, remote sensing, and GIS. Dr. Clarke was chair of the National Academy of Sciences and the chair of the National Research Council Studies on the National Map. He recently served on the Board of Research Data and Information for the National Geospatial Advisory Committee and National Geographic Society's Committee on Research and Exploration. Needless to say, we have a giant in the industry with us. He's taught more students and influenced our industry more than anybody I know. And I've got to say, I had the privilege of serving with him on NGAC. And beyond being a stellar scholar, he's one of the nicest guys I know. His presentation today is on geographic masking, which is the deliberate alteration of locational data to preserve the privacy or integrity of data being displayed or analyzed. For example, the locations of the nests of endangered bird species may be publicly posted on a website, but the availability of this data could create inappropriate visits that could disturb or endanger the birds, and so it should get masked. Today's webinar is going to discuss masking in the context of geospatial privacy, a topic of great national concern in the era of social media and WikiLeaks. Most of the methods in current use will be discussed along with their advantages and disadvantages. How the methods are implemented and what impact they have on geographic and spatial analysis will be explored. Now, I need to please remind everybody, mute your telephones. If you have a question, please use the chat window, and I will submit them to Dr. Clarke at the end of his presentation today. Please also note that GITA is a membership-supported organization. Our ability to bring quality programming and education to all of you is made possible through membership dollars. So if you're not a member already, please do visit gita.org and join now. It's absolutely essential to the continued professionalization of the geospatial workforce. So without further ado, I give you Dr. Keith Clarke.
Thank you for that nice introduction, Talbot, and greetings from a beautifully sunny 72-degree morning here in Santa Barbara. Let me just give everybody a little bit of a sense of why I decided to work on masking, because it's not an area I've worked on much in the past. The motivation comes from serving with Talbot on the National Geospatial Advisory Committee, where the privacy group has been meeting for years, mostly sort of bemoaning the fact that the legalities of dealing with geospatial have yet to really be worked out. In the meantime, there aren't that technological solutions. So I felt that I could contribute perhaps at least one. So in doing the research for this paper, which I'll mention towards the end of the presentation here, I pondered geographic masking and have some information I'd like to pass on. We move ahead with the slides. Today we're going to discuss masking largely in the context of geospatial privacy. I believe it's a topic of great national concern, mostly because social media has transformed the way geospatial data is being collected, and we have an era where transparency and openness and the desire on the internet seems to be widespread. So I'm going to discuss most of the methods, at least currently in use, and some of their advantages and disadvantages. Those advantages and disadvantages primarily lie in propagation of the effects of the mask into further analysis of the data. So you might wonder, why would you analyze data that has been masked? Well, often it's the only data that you have. So how these methods are implemented, what impact they're going to have on analysis will be explored. So what is geographic masking? It's the deliberate alteration of locational data to preserve the privacy or integrity of the data being displayed or analyzed. And this is often identified as having 2 components. One of them is the personally identifying information. For privacy, that might be their street address or their social security number, something that allows you to pinpoint their records. From a geospatial point of view, it's an actual recording of a coordinate where that person is known to live, be planning to visit, etc. So personally identifying information, or PII, is any data that could potentially identify a specific individual. And GIS has enabled us to do what's often termed reverse geocoding, which is to start with a map and then to use parcel data or tiger data, street address type data, to reverse engineer from that data the actual street locations or actual street addresses of the people being represented or the points being represented onto the map. So any information that could be used to distinguish one person from another is also PII, and anonymizing anonymous data can also be considered PII. So reverse geocoding undoes the security that's offered by using PII to begin with. The issues that have largely talked about in the legal context, and this is reflected in several government consent means being or asking the user or the holder of the PII for permission to use their location. We usually encounter this when we're using an app on a cell phone, on a smartphone. It'll say, we want to use your location. Do you agree, yes or no? That is taken as giving consent for use of your locational data. And then use becomes an issue because often data, once they're published, perhaps as a map, can then be used for other purposes than they were originally intended. So perhaps some data were collected as a result of a survey of some kind, with the intent to collect a specific piece of information, let's say for an influenza epidemic. The intent might be to use those data beyond the specific study for which it was commissioned. So we often talk about integrity. These are goals that are mentioned in the GIS Code of Ethics. But integrity lies both with the data provider, but also with the data producer. You might argue also it lies in the hands of the data user, reuser. And these involve accuracy and knowing and verifying specific levels of accuracy. Often this is part of metadata when data are distributed. Validity, which might mean actually making an assessment of whether or not the data has value or has truthfulness. Truth means that we're not selectively applying or modifying the data in any way. We're providing the best data that we have available for a particular problem. And of course, integrity is also related to values. We can quite obviously distort deliberately information by being selective or by adjusting data. So we need to take all of these into account as we start working with data. So let's give some examples of potential misuse. Let's say we have the locations of nests of endangered bird species. We wish to publicly post those on a website. iNaturalist.org is a public domain website that allows you to post photographs of animals. But the availability of this data is going to create, let's just call them inappropriate visits. They could be people just simply wanting to see the birds, but in doing so they could disturb or endanger the birds in some way. And then we could have malicious intent. For example, we could have people looking to capture the birds or kill them. Now, it's not just sensitive biological data that share this potential for misuse. The best examples are in health data, where we actually have federal protections under HIPAA to protect human health records, largely by protecting the PII of the content of the users. Criminal records, the locations or homes of victims of crimes or accidents, archaeological sites where they could be subject to looting. All of these are instances where you would want to protect the data to some extent, and especially to protect the personally identifying information. I mentioned reverse engineering. Reverse engineering has been used successfully in a very early study by Mark Armstrong and co-authors in 1999. He found a map that had been published in the newspaper, digitized the dots of corresponding locations of AIDS victims. To an adjacent segment. I believe some mute their phone. If they could do so, I'd appreciate it. Another good example is a study by Curtis in 2006, in which the exact locations of 55 deaths caused by Hurricane Katrina were identified by street address from aerial photography. I'd argue that's also a violation of privacy. Now, what's brought this issue of masking into the forefront is the ready availability of social media data. Examples of websites or social media that use geotags, or usually getting geographic location into the record, they include Twitter, Facebook, Google+, Flickr, Foursquare, many others that are taking advantages of this new field of location-based services. If we have addresses in the geotag in the data, it's usually going to come from one of four sources. In the case of a smartphone that has a GPS chip, it's coming from one or more global navigation satellite systems. So the iPhone, for example, uses both GPS and the Russian GLONASS system. It can also come from the cell tower location, not quite as accurate or precise, but still can give a location that has meaning. It can come from content. So we might, for example, be analyzing a Facebook page or a tweet that contains place names, and those place names can reveal to a great extent where a person is. Perhaps in Foursquare, somebody's checking into a restaurant. We can surmise that they're actually at that restaurant. Or sometimes the data has been provided as part of the user's profile. So if we go to their profile within, let's say, Twitter, we might be able to extract their home city at least, or perhaps to some other extent the location of a workplace. So from data mining the vast content that we can get from the APIs that are available for querying this data, it's quite possible to relatively simply find a person's home, their workplace, to clearly be able to extract their commuting pattern or other important locations in their life by data mining. And then this data can be linked back to the personally identifying information, which in some cases is also given out voluntarily by the users of social media. So we have a complete violation of privacy. As has often been said with social media, as Scott McNeely said, you have no privacy, get over it. Now, the Bureau, the government agency that has dealt probably for the longest time with the issues of masking is the Bureau of the Census, which, as we all know, does the decennial census in the United States, now completes the American Community Survey every year, so produces a lot of personalized, highly personalized data. It has restrictions in its databases and within its Tiger geographic files in the instance where the number of records or the number of residents within a given geographic entity becomes so small that information such as income or demography could be identified and linked with a single person. In other words, just by data existing for a small area, we can surmise that we can surmise personal information about the individual resident there. The Census Bureau has to retain the privacy of that data for a period of 72 years before it can be released into the public. Past censuses are released usually in block and allow us to analyze personal information about individuals from over 70 years ago. But the rest of the data, and all of the recent data, is protected by aggregation. So the data is kept at the individual level, and it is available for research at the individual level, but only by passing the scrutiny of the Census Bureau and using the data under their conditions and on their systems. So the public, the best we can get is that data aggregated to the block level. The block level representing an individual city block, but obviously blocks get quite large as we go out into rural areas, or can get quite large. These are often then lumped together into block groups. The next subdivision level is the tract, of which there may be hundreds within a city. The minor civil division, eventually aggregation to the county, the state, and the nation. We can normally assume that privacy is being protected when we aggregate to the county, where there could be thousands or perhaps even millions of residents. So we protect individuals by aggregation. So the block group issue becomes a problem when a particular polygon within the Tiger data contains few enough residents that we can identify individuals. And the solution from the census point of view is to aggregate upwards, to not release that block data, but to aggregate it up to the next level. So here's an example from some slides I'm sharing from Oak Ridge on processing census data. Shown in green here are the Tiger files. You notice they're slightly misregistered. And the two numbers associated with them are the block totals of population associated with that group. Now we can see from the photography behind the image that we have in the one parcel that is showing a 0 population, we actually have a housing complex that probably has quite a few residents. And we can see that the Census Bureau has cleverly assigned the 511 residents of that area to the little sliver polygon that's formed by intersection and overlap down the middle of the right-hand side of the screen. So when we aggregate up, the data comes out correct, but we've masked the actual location of these 511 residents. And there are many, many instances of this if you dig around long enough in the Tiger files. So let's look at some of the methods that are used for masking, and these may or may not be present in data that we use on a regular basis. In some cases, it's almost impossible to detect whether or not data have been masked. It's really the producer's responsibility to label the data as masked so that it's not misused. So I'm going to cover each of these methods one by one. We'll look at point and area aggregation, as we just discussed for the Census Bureau, de-identification, affine transformations for data, random perturbation, non-contiguous aggregation, neighbor masking, contextual removal, floating catchments or buffering, and the donut method. And I want to finish with a coordinate-based method that I've recently published. So aggregation is kind of the classic method for disguising or masking geographic data. We have a set of points in red on the left-hand side, original points that might be the locations of, let's say, those birds' nests. We can, instead of providing a set of points, we can provide a single point, perhaps the centroid or a representative point or perhaps the mean center, a location that's not one of them within the sample, but nevertheless represents the sample. So we might simply attach the number of points represented by that point to it as an attribute. Alternatively, we can assign the points to a polygon. This is the classic way that the Census Bureau aggregates into census tracts and census blocks. We just simply designate a polygon that may or may not be the bounding box or the edge convex hull for the polygon. We take all of the points that fall within that polygon, make them attributes of the polygon, and then release the data as aggregated by polygon or by district. In de-identification, which is often a method used in surveys, we delete the fields in the data that show the publicly identifying information. So, for example, names, social security numbers, phone numbers, anything that can identify an individual, we either create a new identifier code or an index which can then be cross-referenced with the actual data that's kept separately, or we can just delete it altogether and make the data anonymous. Obviously, the cross-reference file, which holds the new identifier codes and their cross-references to the PII, needs to be kept secure. So it's not something that would be distributed with the data. It will be kept secure by the data provider. Another example that's fairly common is to leave the PII intact or reasonably intact, perhaps just leave a last name intact, but to mix it up with the spatial information so that the attributes associated with the data are still present, but they're in the wrong order, so we can no longer associate an individual with their exact geographic location. Affine transformations are far more commonly applied than you might think. If we simply take the original points and submit them to a translation, a rotation, or a scaling, so in this case we've rotated them 90 degrees, or we flipped them on the vertical or the y-axis, we've masked every single point. They've been given a new location. And the advantage of affine transformations is that they can leave the spatial distribution of the data somewhat intact. So we don't lose general properties. We might lose specific properties like, for example, the mean center, but we have distribution values or measures of dispersal like the nearest neighbor statistic will still be correct and still be representative of the original distribution, even though all the points have been masked. So the advantages of affine transformations, they're very easy to perform with matrix notation. Most software, ArcGIS, or any of the statistical packages allows you to build the matrices that we need to make the translations. It can be a very effective masking method because it applies to every single point. Obviously, if we rotate about the center of the distribution, those points towards the center are going to be less masked than the remainder. But nevertheless, every single point is altered. It preserves the distances between the points and the aggregate spatial properties, such as the nearest neighbor statistic. But it does lose some spatial characteristics, such as the mean center. And it's relatively easy to reverse engineer because if you can simply try out different reflections or rotations or translations on the data until they match another type of data, such as the tiger files or an aerial photo, then you can quite clearly undo in a single step the entire effects of masking the data. Random perturbation is probably the second most commonly used masking method after aggregation, and this involves taking the eastings and northings of each one of the points and either adding a random amount or doing the same thing by taking an angle from another point and adding, drawing a random angle of displacement and a random distance of displacement. Two can be given as a movement in a direction and a distance, or they can be just manipulated as far as the eastings and northings are concerned. Now, we can make these truly random numbers. In other words, they add a random range to every one of the points, let's say 10 meters, or they could be Gaussian, so we could make them converge around zero so that most points are dispersed at very small distances and only a few points are dispersed longer distances. Now, random perturbation is going to have an overall impact on some of the spatial descriptions, descriptors, and the aggregation effect is minimal, but it depends highly on the amount of perturbation that's used. A very small amount of perturbation of only 1 or 2 meters is unlikely to take a point outside of an individual land parcel, for example. We might have to increase the range to some extent. So here we see a set of points. Let's say the original points are red. We add a random number to the eastings and the northings, and each point gets dispersed to the blue points. We can choose a random number for the direction between 0 and 360, and we can choose a random distance. and we can force them to retain a Gaussian property as far as distance is concerned. So again, most points end up fairly close to where they started. We can do non-continuous aggregation on the basis of areas. This is a fairly commonly used method. So we might have census tract data, for example, that's represented by the orange lines here, an original set of points represented by the red points, which is our sensitive data, and we might do aggregation within tracts or units to a single representative point within each area. So here we'd have different numbers of points, 2, 3, 5, whatever, associated with each of the newly aggregated points. An enormous amount of data is also made available in this uneven area aggregation. We can do non-continuous aggregation also in a linear method, and this is a relatively common method for masking street address data when we have street addresses associated with individuals, with PIIs. So often what we do is we move the points to the nearest block face and then move them to the center of that block face. So this accounts for why Armstrong was able to get such good success rates with the equivalent block face data, is because the data could have been masked to block faces, which would recover all of the data within those units. So again, this is a common technique. It's used in many urban and city-type applications of GIS. Neighbor masking means transforming the points based on the pattern of neighbors. So this is sort of an aggregation effect. We can choose points such as on the left-hand side where we have the original points, the unmasked data in red. We can place a new point representing a cluster or an aggregation in the unmasked data and then assign the attributes to that point. Again, none of the blue points here represent an actual red point. They're all at new locations. Or another effect that we can do is to move neighboring points either together, as on the left-hand side, where we can just draw points together but keep their PIIs, or we can move them apart. So in the lower right-hand side, we've taken the red original masked points and moved each point away from the cluster in its opposite direction. So this moves the points further apart. It obviously affects the spacing between the points, so we get different nearest neighbor statistics as a result. So overall, the pattern distribution looks similar and so retains some of the spatial properties of that distribution. Another trick that we can use is contextual removal. So we may have data being served out, let's say, on a web interface with a reference base map underneath, perhaps an image or OpenStreetMap or the Tiger files themselves. If we have a frame of reference, such as an air photo, we can begin to associate a point with an individual house. But if we remove that context and just treat the points as a random or as a point distribution in space, by context removal, we remove on a map, we're removing some of the information that allows us to identify the individual points. So contextual removal has been used in many social media applications, or we can also generalize the underlying map to a level where the individuals are hard to locate with a particular location. The method known as buffering involves laying a buffer over the information source, the feature that's giving the context. In this case, let's say the street map. We create a buffer of a certain size, and then any point that falls in the buffer, we move to another location outside the buffer, but still in the vicinity of the original point. So if a point falls outside the buffer, we leave it intact. If the point falls in the buffer, we disperse it, move it away towards the center of the block. And this is particularly appropriate where you have rural areas with houses located along streets, where the points associated with the houses are quite close to the street. buffering using the streets allows the points to be moved into a less conspicuous location somewhere in the center of the block. The donut method is intended to remove points within a threshold. So we decide upon a threshold radius. We take the actual point and look for points that fall within the threshold radius. If we find such a point, we move it outside of the threshold radius. So this is a way of enforcing a lack of contiguity or taking points that are close to each other and moving them further apart to make the identification more difficult. So here we have 2 points that fell within the threshold. We've moved both of them outside of the radius, and now we've masked those 2. We then simply repeat this process for all points. Again, we alter the entire distribution. The method is essentially not reversible. Once we've applied it, it's impossible to get the original data back again. So let's look at some of the issues surrounding the masking problem. We should ask of a method, does the method depend on specific parameters such as distant thresholds or particular random number sequences? We often use random number generators to associate random perturbations with the data, but random number generators themselves are subject to repetition. We have to be very careful about seed numbers that are used for generating what are called pseudo-random number sequences. We would like those to be as impossible to retain the sequence or to get the sequence back by using a particular piece of code. So a second issue is, does the method achieve the goal of obscuring the actual sensitive locations? As we've seen, some of the methods, like the buffering methods, will leave certain points intact. So we have to decide whether or not leaving those points in their actual locations represent a threat to the privacy or to the PII. And we should ask, can the method be hacked? As we saw in the Armstrong study, simple reverse geocoding is often enough to get the data back again. But if we can be a little bit more intelligent or know something about the masking method that's been applied, it may be possible to undo its effects and reveal the original locations. What is the impact on the mapping and further spatial analysis of the data if the data has been masked? As we've gone through the various methods, I've implied that some of them will provide different bounding boxes for the data. They'll provide different centers, mean centers. They might provide similar standard deviations of distance or standard distances. They might produce identical spatial descriptors, such as the standard deviations, but they may not. So if there's important spatial analysis to be done, and there often is for data like biological data, then we have to suffer the consequences of possibly corrupting that data. We have to ask, how complex is the process and how long does it take? Do we have to invest CPU time in encoding the data? And how many steps are there? Is it simply a script which can be run on the data? Or is it a complex numerical process that might run for several hours? So how much time and effort do we have to invest in applying the method? And then the last issue is one of invertibility. If I hold the original data behind a firewall and give out masked data, the user may have good reason, or eventually will always have good reason to want the original data again. If we now have both a masked and a original version of the data set, we've got a data management problem in what data has been published, which is available and distributed versus which has been restricted but may be made available at some later time. So the ability to invert a method, that is to start with the masked data but apply some kind of unencoding method to retrieve the original data, could have a distinct advantage because any potentially distributed version of the data set now has the capability of getting back the original distribution, should it be necessary. So let me make some comments finally about my method that I've just published. This has just appeared in the International Journal of GIS, volume 30, number 3. There's the DOI if you want to go straight to the file. Note that one of the tables had to be corrected, and there's also a published correction that, to that one table. The paper is called a multiscale masking method for point geographic data. The multiscale aspect is one of the keys to it. It applies across scales, and we can choose in applying the method what level of dispersal we want. We'll show you just how in just a second. The actual method itself is implemented in the C programming language. It involves some code that takes as input the military grid reference system coordinates and encodes them into a new file. It takes advantage of the GEOTRANS package. GEOTRANS is an excellent coordinate conversion and map projection set of utilities and libraries published by the NGA and supported through multiple versions online. And it will pretty much do anything you want as far as coordinates are concerned within GIS. So my method is invertible. It's perfectly invertible. I'll show you how in just a second. It applies across scales, so you can decide how much perturbation you want to give to the data, and is based, as I said, on the military grid reference system, the standard set of coordinates that we use for the U.S. military and for NATO, but also implemented in the United States as the national grid, although there we use NAD83. So let me define the problem specifically. Given a set of point coordinates in which we have eastings and northings and potentially a large set of points, usually in the hundreds or thousands, or in the case of social media data, sometimes in the millions, we would like to adjust each point so that its original location cannot be retrieved, and so we completely sever the contact between the geospatial data and the personally identifying information. And the methods that it applies, or that can be applied, as we've seen, can be aggregation. We can use anonymization. We can use affine transformations or random displacement. Any of these methods will work. Mine is simply an alternative. So here's an example of a location. I believe this is my office in the military grid reference system. So 11S KU 38488 11890 really separates into 3 parts. The black part of it is the what could be thought of as the metadata leading to the location within 100 kilometer square on the Earth's surface. Then we have what's shown in green, the easting associated with the data, and in red, the northing. So the entire flow diagram here involves taking our data in geographic coordinates on the upper left, subjecting it to GEOTRANS to translate it into point data in MGRS. We then run the code which masks the point data, and it produces, in fact, 2 files. One, the actual reflection of the point data file. So if there are 1,000 points in the MGRS file, would be 1,000 points in the mask file, but also spits out a single code which allows the data to be reversed or recovered. If the code and the mask data are placed together with a new program called Reveal, it will recover the exact MGRS and allow you to transfer those back into latitude and longitude. So the military grid reference system, most of you will be familiar with this, but the way it works is we divide the Earth up into these 60 UTM zones, numbered from 1 to 60, starting at the 180th meridian and increasing in number as we go from west to east. Within those, we have a second set of numbers that are called grid cell designators. So we divide up the 6-degree wide cells into blocks of 8, or in one case 12 degrees, and assign letters to those. We then have a separate numbering system shown here on the blue diagram in the upper right for the area surrounding Hawaii, where we have identifiers for the cell squares. You can see the DM identifier for the cell square that falls surrounding Chicago, for example, on this image. These occur and are reproduced on the on the national map. So if we retrieve the metadata, what's called the color information from any of the quads on the national map, it'll give you the UTM designators. And then we have simply an easting, which consists of 5 digits, and a northing consisting of 5 digits, the largest value being 99999, filling all 5 digits with 9, and therefore representing values from 0 to 99999, or the 100 kilometers. So step 1 in the encoding process is to use GEOTRANS to take the original datum, which has latitude, longitude, and the datum. The datum is important because we're going to use GEOTRANS' .dat format. The converters for that as part of GEOTRANS. And we're going to convert the data to MGRS. If you want to see GEOTRANS in action, the website is there. It's under earthinfo.ngo.mil GNG/GEOTRANS, or you could just Google it and find it that way. So then I use customized procedure, and this is the way it solves the problem. It has 10 digits to replace, 0 through 9. Each digit will need to replace with another digit. So let's say a 1 might be replaced with a 5. But the choice is narrow for a choice of other digits as we select more and more digits. So if we take into account all the possible combinations of replacing each digit with another digit and not reusing any digits, we end up with 1.3 million possible combinations that assure that all digits are altered. So my method tries every possible combination, but with replacement only for specific digit places, as we'll explain in just a minute, and it uses brute force. In other words, it calculates all of the values, and in each coding, each iteration, it computes a set of metrics for the new point set and compares that with the original. The values that it actually computes involve the extremes, the bounding box, the minimum max, the means, the medians, the standard deviations in X and Y. And then it also calculates the nearest neighbor statistic representing the dispersal of the distribution. It takes all the mean differences, the tiny differences between those, multiplies them by the difference in the sum difference for the nearest neighbor statistic, and it retains the specific numerical code with the smallest difference from the original point set statistics. So here's the table 1 from the paper. You'll notice that we have the digits 0 in the lower left-hand side, the blue part. We have the digits 0 through 9, and on the right-hand side in red, we have the value that's going to be switched to. So 0 is going to be switched to a 9, a 1 to a 7, a 2 to a 5, and so on. On the top, we see a coordinate given with its key code. So the code key actually looks like a MGRS reference coordinate, but in fact, it's the master reference. So in red, you'll see the same numbers that I just read off as in red on the lower left. So on the bottom right, we show how this is applied one step at a time, replacing each digit and ending up with an encoded MGRS value.